Welcome to this video. We are going to learn why light refracts, and we're going to learn how to figure out which way light will bend when it goes into a new medium. First, let's make an analogy to a car driving on a road. Here's a car, and right now it's on a road, but it's headed for this mud patch. Now, when the car reaches the mud patch, it will slow down. But notice, this tire will enter the mud patch before this tire. And so, this tire slows down, while this one keeps going at the same original speed. What happens is that we now have half the car going at a slower speed and half at a faster speed. This has a particular effect. The slower tire right here serves kind of like a pivot point, and so the car turns around. The faster moving tire swings on a bigger circle, and the slower moving tire, in the same time, goes along a smaller circle. If we let a little more time pass, the car bends further, and now this second tire finally enters the mud. When the second tire enters the mud, it slows down to the same speed, and now the car just moves along the same line because both tires have the same speed again. So what we notice is that the car starts along some original path, and because it slows down, it changes and it bends to a new path. There's our summary. The same thing happens with light when it goes from one medium and slows down upon entering another medium. The thing about light, though, is it doesn't have tires. Light has wavefronts, and we show those wavefronts with these lines that look like rungs of a ladder. The wavefronts of light are similar to the wavefronts of sound. When we strike a tuning fork, a sound is produced. The sound consists of these compressions, which we draw with solid lines or wavefronts. So what do the wavefronts here indicate? They don't indicate compressions because light doesn't have compressions. Instead, they indicate the crests of the wave. So the light wave has this wavefront, and what happens is that half of the wavefront enters the water while half is still outside of the water, just like having half of the car slowing down and the other half staying at the same speed. So because the half that enters water slows down, the half right here produces this bending. So where the car originally is moving along this angle and then it bends to this angle, the light does the same thing. It begins along this angle and it bends and moves along this angle in the end. We draw just those arrows. Those are called the rays, and they indicate which way wavefronts are moving. We usually leave out the wavefronts altogether because the picture gets a little complicated. So here's our picture showing light refracting as it goes from medium 1 to medium 2. This big bold line across the middle is called an interface. It represents the boundary between the two media. So everything above this bolded line, everything above the interface, is air, or medium 1, and everything below is medium 2, or water. The dotted line is called a normal. We call it a normal because this dotted line is perpendicular to the interface. And in mathematics, normal is another word for perpendicular. Every medium has a refractive index, which is given the variable n. The refractive index measures two things. One is it measures how much light bends toward the normal. And the second thing it measures is how much light slows down. We use angles to indicate how close light is to the normal. Look at this. This is a medium angle. So light is kind of close to the normal. Down here, that's a smaller angle, so this ray is even closer to the normal. Two rules help us solve problems. The higher the value of n, the closer light travels along the normal, or to the normal. The slower the speed, the closer light travels toward the normal.